right, so yeah, today I'd like to discuss with you a new auction design that we plan to implement at KAO Protocol, and a little bit of kind of the thinking process behind it. So how did we get to this specific auction design, which has to do with the fact that, blockchain is an environment where there may not be a numeraire, and of course I'll explain what it is in a second. All right, so many talks that has to do with DeFi start by saying, okay, look, we have all these mechanisms from traditional finance, but they don't necessarily quite apply to our environment because, say, in the context of blockchain, transaction can be reordered, and therefore we have MEV. I'm going to follow a similar template, but I'm not going to focus so much on the usual suspects, and instead focus on a different element, which is the absence of a numeraire. First of all, what is a numeraire? A numeraire is an asset that in your market or in your mechanism, your environment, you can assume that everybody likes and is happy to receive and can be used to share value between people. Okay? Now, off-chain, there is usually a numeraire in the environments you consider. If we want to look at financial markets, well, typically all stocks are traded against the national currency. So the national currency is the numeraire. A possible exception could be forex market, where people exchange national currencies. But when you look carefully, that's not quite an exception, in my opinion, because first of all, there are very few assets exchanged. And then, essentially, the vast majority of these trades is anyway settled against the US dollar. So it's even in that environment, there is, theoretically, there's no numeraire. Anybody may be demanding different assets and exchanging any currency for any currency. Really, most of the volume goes through the dollar anyway. Now, on-chain, things are very different. There may be specific environments where you can assume that there is a numeraire, but I think in general this is not, it may not be the case, because we have anonymous participants that could live anywhere in the world. When you look at financial markets on chain, people may want to swap any asset for any other assets. There are like thousands. I don't know if there is a number out there. I know that KAO Swap in its history has traded more than 11,000 different tokens. So there are at least that many different tokens on chain at the moment, and probably even more, which makes it very different than in any kind of the forex market, for example. Also because here what matters is not the number of tokens, it's the number of token pairs. So that kind of blows up the complexity of the problem. So why does this matter? Because the numeraire and the absence of the numeraire determines how easy it is for people to share the benefit of collaborations. Okay, this is something that we know from a branch of game theory called cooperative game theory, which is the branch of game theory that has nothing to do with auction, in fact. But it turns out that it also matters when you're designing certain type of auctions, such as trade intent auctions. Now, what is a trade intent? A trade intent is essentially an order in which a user specifies a sell token and a buy token, and might specify also a limit price or a slippage tolerance. And then it delegates to another agent, a solver, the exact execution of that order. And this is done in the context of an auction, where solvers are going to propose prices for each order, for the different orders. And let's say, the details are important, but for the moment, let's just say that the solver that proposes the best price wins the auction and then has the right to complete this order and actually execute it on chain. Okay? Now, this is an environment where you can have separate auction for different trade intents. Okay? An order comes in, you run an auction. Another order comes in, you run an auction. And this is how protocol like 1inch Fusion and Uniswap X work. However, there are typically additional efficiencies when orders are executed together. This could be in the form of coincidence of wants. Maybe people can trade directly with each other without really having to access an external market. It could be in the form of gas savings. Coincidence of wants can also arise as an intermediate hop of trades. Anyway, generally you can squeeze out additional efficiencies by executing trades together. But of course, the problem becomes in which assets those efficiencies materialize. Maybe it's extra ETH, because it's gas savings. Maybe it's something else. But then not everybody may actually want the assets in which those efficiencies are actually generated. And the question becomes then, how do you share those extra efficiency if it's in an asset that not everybody is demanding? Okay? And then, then the question becomes, well, do you want to execute the two orders together, even if there are efficiency, because you cannot really share them? And if you do, then what is the fair share of this extra efficiency? These are the type of questions that motivated our research paper that I wrote with a colleague at CowSwap called Felix Hanneke, where we build a theoretical mathematical model of this type of auctions. We use this model to compare the two most common auction formats, which is batch auction and separate individual auctions. And then we use the model to then propose and study a new auction format, what we call the fair combinatorial auction, which if you want, I'll get in the detail later, but it's a kind of a merge between a batch auction and kind of having separate individual trade auctions. And this is a bit like cooking. They say you're putting two things together, whether you generate something with nice property or not, kind of depends on how you do it. And it turns out that if you do it in a specific way, this fair combinatorial auction can actually provide strong fairness guarantee. So you have a notion of fairness that has to do with how the efficiency from batching are shared, and that the auction can guarantee. If you do it some other ways, you have absolutely no benefit of doing this. Now, for today's discussion, I'll just give you a high-level discussion of the two most commonly used auction formats for trade intent. And I will discuss then the fair combinatorial auction in the case where it does provide fairness guarantees, okay? But knowing that if you change the design, you should know that maybe it does not provide any fairness guarantee anymore. And the QR code here is the link to the paper if you want to kind of dig into the mathematical details and the additional results there. All right, and by the way, to reiterate, this is something that we are planning to implement at Cow Protocol. So this will be live at some point in the next few months. All right, so let me start with how things are done currently at Cow Protocol. Cow Protocol runs a batch auction that works in the following way. And apologies for the bit primitive kind of graphics here. So there are users that come in and submit orders. These orders are added to an order book. And at time intervals, which correspond to the closing of a batch, the auction starts, and solvers can bid on groups of orders or even individual orders that are on the order book. Okay? Solvers may be somewhat specialized in certain type of orders, so they don't need to bid on the exact same order. And however, they can submit a single solution, and which here can be a collection of orders with prices for those orders. Now, they then send the proposed prices for the orders that they want to execute, and then the auctioneer ranks this proposal by the total value returned to user. We have a concept called surplus, but for today, this is, you just can think of it as just really the total value of the asset returned to users. This requires some price feed, of course, because one order may want to buy Doge, the other order may want to buy something else, and solvers might propose different execution. If you want to be able to compare them, sometimes you need to have a price that allows you to rank those solutions. Okay, and okay, there is one winner, and this one winner goes and executes the solution on chain, and the other solvers, okay, they are losers, they don't get anything. Right, this is the batch auction. There are a number of additional rules. For example, uniform clearing prices. If you have the same token pairs in the batch, then so all traders trading on the same token pair on the same batch must have the same price. But for today's discussion, this is not too important. Okay? So this is a summary of what I just said. Now, compare this with what other people are doing. The other people are essentially running trade-by-trade Dutch auction. Okay, the fact that it's a Dutch auction is not too important, but this is really just separate auctions for each trade that comes in. Okay? And just to give you some numbers, if this market handles about more than $5 billion of value each month, I think bit 3 of them is like Cow Protocol, so goes through the batch auction mechanism. And the remaining part is split with the other two, so the remaining part is executed using these individual Dutch auctions. All right. What are the pros and cons of each mechanism? Now, obviously, batch auctions are better at exploiting whatever complementarities and additional efficiencies there are when you get to execute multiple trades together. Coincidence of what's, gas saving, so on and so forth. Precisely because the solver has the view of the entire order book and can actually, in the solving logic, start thinking, oh, look, if I take this order and this order and this order, maybe I can make a ring trade, example. This is not possible to do if you have separate auctions. Now, but on the other hand, if you have separate auction, there is a benefit there because you can allocate different order to different solvers, even order that are received at the same time. So say that you have a type of order for which one solver is very good, another type of order for which another solver is very good. You can specialize. You can give one order to one guy, the other order to the other guy. But in a batch auction, you always have one solver winning potentially multiple trades. So it's harder to exploit this benefit from solver specialization. Now, batch auction, this is we show in the paper, and it was, maybe you need the mathematical model for that, but one result is that the batch auction is better at generating competition between solvers, because again, if you have somewhat specialized solvers and run these individual auctions, each on one auction per trade, then really just the solvers that are good at that trade will compete. Okay? You have a subset of the solver in each auction, essentially, where the batch auction forces everybody to compete with everybody else. So there is a higher competition between solver and more value returned to the user in general on batch auctions. And on the negative side, like in batch auction can be unfair if you're not careful, let's put it this way, because in the vanilla batch auction, you are just ranking solution based on this total value, and you're kind of oblivious to the fact that perhaps, this total value is very high, but one guy is getting a pretty shitty deal, and another guy instead is getting a great deal, and maybe that's not something that you want. Okay, you aggregate everything and you don't see it. Now, the way this is currently handled at Cow Protocol is through a thing that we call EBBO. Essentially, we have a routing algorithm that checks after the fact whether the execution of each order was better than our own routing algorithm. And if it is not, we call up the solver, we tell him off, and we ask him to reimburse the user for this kind of EBBO violation. And the hope is that then they will be more careful in how they actually split the benefit of this, so how they allocate value between the users. This is time consuming. It is a vector of centralization. We'd like to be more decentralized. And also from a more like game theoretic mechanism design perspective, it uses information available to us. So it's our routing algorithm, but the experts here are the solvers. So we are building this reference for fairness from our information, but we are not the most informed party here. The solvers are the experts. So we'd like to instead build a mechanism that elicits this reference for fairness from the solver themselves. Yeah, and therefore, each mechanism has its pros and cons, and therefore this really begs the question, can we really think of a third type of mechanism where you might have in equilibrium either batching or specialization. So it leaves open the possibility of having batching or specialization depending on what is the most efficient thing to do in that context. It generates competition between solvers and has a notion of fairness. So you can define fairness and say, okay, the outcome here is fair. And this is exactly the fair combinatorial auction. It works in the following way. First, it's a combinatorial auction, so it allows multiple bids per solver. So solver here can submit, a single solver can submit, say, a bid for order 1, which is how many tokens I'm willing to return if I only win order 1, a bid for order 2, a bid for order 3, but also a batch bid. Say, okay, but if you give me the 3 orders together, I can generate so many tokens for the first guy, so many tokens for the second guy, so many tokens for the third guy. So this is a multiple bids per solver. And then the important step here is a filtering of batched bids, where what you do is the following. You first consider only bids on individual orders, okay? And then you ask yourself, well, suppose I have really separate auctions, one for each orders, and those are the bids in that auction, and say that the auction is in first price, how many tokens this guy would have received, okay? This is then the reference for fairness, okay? Because you say, well, you know, if I was really to just have a first price auction on order 1 with the bids that I got, order 1 would have received that. And you use this and repeat for every order, and you use this reference to filter out batch bids whenever the batch bids propose an execution that is worse for at least one trader relative to this fairness benchmark, right? And then at the end, you have some surviving batch bids that were not filtered out, and you have a bunch of individual trade bids, and you want to recompose a solution with multiple bids in a way that maximizes an objective, for example, total value that you return to the users. If this was fast, let me bring back the great graphics I had earlier. Here I have two solvers. And importantly, they are allowed to submit multiple bids. In this example, solver 1 has, so each solver here has 3 individual bids, okay? Solver 1 sends 1 individual bid on the green order, an individual bid on the yellow order, and 1 on the red order. This says, I'm willing to return to the green order X many token if I only win that order. Similarly, solver 2 sends some individual bids. And then in the example, each solver sends 1 batched bid, which contains a collection of orders, okay? And typically, the amount returned in the batch bids for the same order might be different than the amount returned in case the solver wins only that order. Then you construct your reference outcome. As I said, if the auction is first price, essentially you always want to just take the maximum of the individual bids, okay? That's the reference outcome. You use the reference outcome to do the filtering. So you say, okay, in this batched bid, is any of those bid value lower than what the guy would receive if I was to consider this outcome instead? And in this example, let's say that the first bid, the batch bid from the first solver survived this filtering. So it's fair, quote unquote, relative to this reference. While the batch bid of the second solver does not, perhaps, I don't know, in the yellow order, what solver 2 proposes here is worse than what the yellow order will receive if you just looked at the individual bids. So it's filtered out. And then finally, you have, this is the composition of the winner. You have the solver 1's batch bid together with solver 2 individual bid on the purple order. Okay? That's how you reaggregate everything in the end. Now, this is a new type of auction, so you really need to study, okay, and it sounds maybe good in practice, but then you really need to be careful in what is the strategic consideration that solvers are going to make when bidding in this auction, and therefore what is the equilibrium that you expect to emerge. Now, in terms of strategic consideration, there are 2 important things. First, if you compare bidding on these individual trades here to simply having separate auction per trade period, here there is a higher incentive to bid in the individual trades bids because you anticipate that the way you bid on the individual trade will be used to determine the reference for fairness and might end up kicking up your opponent batched bid as unfair. So typically you want to bid higher in this individual bid than you would do in the standard like simultaneous auctions. At the same time, you might bid lower here in the batch bid, like lower value, than in a standard batch auction, precisely because if you expect the other guy's batch bid to be kicked out as unfair, then you don't need to bid that high because you think there's going to be less competition. The composition of these 2 effects generates an equilibrium that in which you have fairness guarantees, meaning that in equilibrium, each solvers always return strictly more to the traders than if you had done a standard kind of simultaneous first price auction, this separate auction. So it's always better for everybody than having the individual auctions. You may get batching or specialization depending on the relative benefit. It could be that different solver wins different order or one solver wins a collection of order, depending on which is more efficient. And it is, however, true that there is, if the equilibrium is batching, the winning solver might return less to the traders than in the batch auction. So in a sense, the takeaway is that this auction format generates fairness guarantees, but this is sometimes at the expense of total value returned to the user, which if you think about it makes sense because here, if you just wanted to maximize total value, you should just do a batch auction. Here instead you are introducing a second element, fairness, and of course the second element means that sometimes you are trading off a bit like on the total value you are generating. So to summarize and conclude, trading intent auction are cool and they're the future. Like this is a shorthand to say that they're really at the center of many of the discussion we are having in these few days. They're a center of discussion about MEV. They're a center of discussion about liquidity fragmentation. Now there is this extension to cross-chain that is slowly materializing. So it's also the center of the discussion about a kind of chain abstraction and all that. So they're really kind of very important element, I think, in DeFi and blockchain in general. Usually there are efficiencies from batching, but of course then how do you share this efficiency is not obvious. There are fairness is a concern, and here is a proposed solution, the fair combinatorial auction, which hopefully should be live in a few months. Thank you.
Thanks, that was a very meaty talk, and we have equally meaty questions. In the current version of CowSwap, why do solvers make bids on subsets of pending orders and not on all in one batch at once? Is it possible for a solver to make multiple bids right now?
So, I mean, I don't know if it's technically possible, but it doesn't really make a lot of sense right now because anyway, there's going to be a single solution chosen. So if a solver comes up with multiple possibilities, it should just return the one possibility that generates the highest value because that's how the auction will rank all the solutions. Okay.
The next question is this model scalable? You have true raised to n possible batches each time. Can solvers manage the load?
Excellent question. So there is a general question about combinatorial auction have this thing called winner determination problem. So the computational complexity of the problem can expand a lot. Now, this is why I said here the important part is from the auctioneer is the filtering part. Okay, so you want to remove some bids from the auction based on this fairness argument, which on the one hand should make the determining the winner easier. Okay, because you have fewer bids to work with in the recomposition stage, and it's also somewhat orthogonal in exactly how you want to do it. You can use some heuristic to determine the collection of bids that wins, which might not be the exact optimum, but it's easy to calculate. And this is similarly with the solvers. Of course, there is a theoretical optimum that require a lot of time to calculate, and in the same way as the auctioneer will use some shortcuts to make everything manageable, the solver should come up with some shortcut as well.
Your auction doesn't seem incentive compatible, so the first price is not a good measure of fairness. Bidders could also bid non-monotically.
I disagree. So I can assure you this is not nothing research. That is a 30-page paper with all the proofs. So unless this is incentive compatible in some non-obvious way, but in terms of deriving the optimal bids, the best responses, and the equilibrium, I can assure you everything is there and shown.
Can solvers pretend to be users and game the batch?
So this is an excellent question that doesn't quite apply to the discussion I had. It's true that it applies to another aspect of a CowSwap batch auction, which is that now there are solvers receive rewards from the protocol. Because of these rewards, it could be the case. There are attack vectors, such as the one discussed here. But in a sense, I didn't discuss rewards, so let me not bring up this thing now.
Does it make sense to decentralize the auctions behind Cow? Are you working in this direction?
So it makes sense, and we are working in this direction.
How will you order different solver solutions in one batch?
So excellent, yeah. So you could have, it's a tricky problem because obviously the first solution gets an advantage when executed. In a sense, so the problem is that a solver observes the state on chain and then submits a solution. Then, next block it goes and executes the solution, but then other thing happens before the solution is executed that might actually change the state of the blockchain, for example, the liquidity available in AM, and make the solution proposed not executable anymore or more costly than expected, blah, blah, blah. So in a sense, there are zillions of things that might happen from the moment where you think of your solution and when the moment you execute it, which means that you need to be kind of conservative, okay, when you propose a solution. And now you need to be a little bit more conservative because among the zillions things that may happen before you submit your solution, there is a zillion plus one, which is another solver also submitting his solution. So yes, it introduces some additional risk for a solver in an environment that is already fairly risky. And so, yeah, just general advice is to solver, be conservative, anticipate that things might change from the moment where you choose your solution and the moment where you execute your solution.
Is there a public record for historical EBBO?
EBBO prices or EBBO violations? EBBO prices, I don't think so. EBBO violation is an excellent question. These are on-chain transfer done by solver just to a user a bit out of the context of a batch. So this is for sure recoverable somehow, but I don't know if there is a easy to access repository or data that one could do. But
so we are out of time, but there are at least 4 more questions that I can see. It is lunch break now, so you can easily go and talk to Andrea as well. But it was a really meaty talk and we all appreciate it, and thanks.
All right, thank you very much.
So we'll be back in 1 hour at 2:30. So another 3 talks. This is the MEV room for anyone interested.